तो कल हमने एक थ्योरम की थी. लेट्स रिकॉल इट स्टेटमेंट फर्स्ट. The theorem was, we had shown that the dimension of the vector space LVW, the set of all linear transformations between two vector space L, V and W, is equal to dimension of V into dimension of W. Okay, now we will define certain more things in this. जो हमने कल भी स्टार्ट किया था, the invertible linear transformation. So the definition is a function t from V into W is invertible if there exists a function some t dash from W into V such that t into t dash. Now this will be a function from W into W is the identity mapping map on W, and t dash into t. Now this will be a mapping from V into V is an identity map on V. Is an identity map on V. तो इस तरह की function को कहते हैं invertible function, or we can also call it as a non-singular function. So now let's have a little result on this invertible functions. So we shall do it again in the form of theorem, and it states that let V and W are two linear transformations, two vector spaces, and T from V into W is an invertible linear transformation. Invertible linear transformation. Then the inverse of T. Then the inverse of T is also a linear transformation. ठीक है. तो अगर हमारे पास कोई linear transformation होगी and its inverse exists, then the inverse transformation is also a linear transformation. तो इसका प्रूव भी करें हम या आप खुद करेंगे? Okay, so let us do the proof. So we are given that T from V into W is linear. That is, T of alpha V1 plus V2 is always equal to T alpha T of V1 plus T of V2. This is what we mean by saying that T is a linear transformation. We have to show that T inverse is a linear transformation. So let T inverse denote the inverse of T. Denote the inverse of T. Now let's choose some two elements. So actually what we have to do, हम पहले हम वो लिखेंगे हमें करना क्या होगा. We have to prove something like this. T inverse of something alpha W1 plus W2. हमें ये दिखाना होगा. This is equal to alpha T inverse of W1 plus T inverse of W2. ये चीज हमें दिखाना होगा. तो इसके लिए हम पहले चूज करेंगे some elements from W. Now let W1, W2 belong to W. So then, since T is owned, because T is invertible, so it must be 1, 1 and owned to. Since T is owned to, thus there exists V1, V2 belonging to V such that T of V1 is equal to W1, T of V2 is equal to W2. This directly comes from the definition that T is invertible and so T is owned, so therefore every element has a preimage. So we have defined the preimage of W1 and W2 as V1 and V2. Okay. So now we have this thing. Now T of alpha V1 plus V2, as we know that T is linear, this is equal to alpha times T of V1 plus T of V2. But now T of V1 is equal to W1. So this is equal to alpha W1 plus W2. So thus, alpha V1 plus V2 is the preimage of alpha W1 plus W2 under the linear transformation T, under the linear map T. Okay. And so we must have this T inverse of alpha W1 plus W2. This is equal to alpha V1 plus V2, and this directly comes from this equation. So, but now this is equal to alpha and V1, we know it is equal to T inverse of W1. And then plus this V2 is equal to T inverse of W2, and the proof is complete. So thus, T inverse is a linear map. ठीक है? Now let's have one more definition. Singular and non-singular linear transformations. Singular and non-singular linear transformations. And how we define these singular and non-singular linear transformations? We define a linear transformation T from V into W is singular if T of V is equal to 0 implies V is equal to 0. That is if nullity of T is the 0 vector. So अगर nullity of T सिर्फ 0 होगा, then we call such a linear transformation. It is called a non-singular, not singular. It's called non-singular. ठीक है? It's called non-singular. So a non-singular transformation is the one which only maps a 0 vector into a 0 vector. That means if the kernel of such a mapping is equal to 0, then such a linear transformation is always called non-singular. In fact, we know that a necessary and sufficient condition for nullity of T is equal to 0 is that the mapping is a 1-1 mapping. That means every 1-1 linear transformation is a non-singular transformation. तो उसके बाद जो अब linear transformation non-singular नहीं होगी, then that transformation is called a singular linear transformation. So thus evidently T is 1-1 if and only if T is non-singular. Because we know that T is 1, 1 if and only if nullity of T is equal to 0. But now we are defining that a transformation is non-singular if its null space is equal to 0. But this is a necessary and sufficient condition for a mapping for a linear transformation to be 1, 1. And so a linear transformation is 1, 1 if and only if it is non-singular. So further, if a linear transformation T is not non-singular, then we call it singular linear transformation. Then we call it singular linear transformation. ठीक है? So now let us define a Mlf example. So let T be a mapping from suppose R square into R square defined by T of xy. This is equal to suppose simply xy. Then this is an identity mapping, and so it is a so only the 0 vector will be mapped into a 0 vector. Then clearly T is non-singular. होगी ना non-singularity, because this is just the identity mapping. Every vector is mapped into itself, so it is only the 0 vector that will be mapped into a 0 vector. So therefore this is a non-singular linear transformation. तो इसी तरह से suppose example number 2, a mapping T from suppose R3 into R3 defined by T of x, y, z. This is equal to suppose let's call it z, y, x. Now what do you think? Is this transformation a linear transformation or not? Now is this transformation non-singular or not? तो क्या लगता है आपको?
Non-singular.
Exactly.
Non-singular.
Then
Non-singular.
T is non-singular. So T is non-singular means that T is 1, 1. Now is this mapping onto? That is T is 1, 1. Now is this mapping onto or not? हाँ बताइए, ये मैपिंग है onto या नहीं है? पहले वो कल के रोल नंबर्स जो मिसिंग थे, व्हाट वर दोस? उसमें 7 और 40 ने मुझे बताया था कि उनका क्या इशू था, लेकिन बाकी लोगों ने नहीं बताया. सो लेट मी चेक देम एंड वी विल रिमूव देम फ्रॉम हियर. हाँ आप तब तक सोच लीजिए, इज दिस मैपिंग ऑन टू और नॉट?
Yes, sir.
हाँ बताइए कोई रीजन?
Because it is invertible.
Sir, pre-image है हर कोई.
Range of T equal to W.
Domain and codomain are
Yes, sir.
एक हाँ क्या है डोमेन और कोडोमेन? व्हाट इज दैट?
Yeah, sir, same.
Sir, it is a linear transformation. It is
So
on to
pre-image है हर कोई element.
हाँ एग्जैक्टली दैट इज ऑल्सो ए गुड रीजन कि हर एक एलिमेंट की प्री इमेज है. सो आप बता सकते हो कि मतलब एक एलिमेंट की प्री इमेज किस तरह से डिफाइन होगी यहाँ पे? तो अगर हम कोई एलिमेंट इस कोडोमेन से लेंगे, सपोज हम एलिमेंट ए बी सी, तो जो उसकी प्री इमेज होगी दैट विल बी सी बी ए. ठीक है,
CBA, इसका रिवर्स है.
कर सकते हैं. हमने एक थ्योरम की थी दैट इफ वी हैव अ लीनियर ट्रांसफॉर्मेशन बिटवीन टू equal dimensional vector spaces each having a finite dimension, then a mapping is 1 1 if and only if it is on to. जो हमने वो equivalent तीन parts किए थे, 1 1 and then on to, then rank of T is equal to dimension of V. So if we have a linear transformation between two vector space of equal finite dimension, then T is 1 1 if and only if T is on to. तो वो भी हम यहाँ पे reason दे सकते हैं that T is non-singular means that T is 1 1, and but since there it is a mapping between two equal finite dimensional vector spaces, so this mapping is 1 1 if and only if it is on to. तो किसी ने कहा था this mapping is invertible, but invertible does not mean non-singular. Non-singular just means that nullity of T is equal to 0. Now since so clearly T is on to. ठीक है, तो यहाँ पे एक हम प्री इमेज डिफाइन कर सकते हैं. अगर हम कोई भी एलिमेंट आर क्यूब से लेंगे कोडोमेन स्पेस से, एनी एलिमेंट सपोज ए बी सी, तो जो उसकी प्री इमेज होगी दैट विल बी इसका रिवर्स सी बी ए, बिकॉज दिस टी ऑफ, सो एक्चुअली इफ वी चूज, सो इफ सम एलिमेंट सपोज ए बी सी बिलोंग्स टू आर क्यूब, और यहाँ पे आर क्यूब को हम लिखेंगे कोडोमेन, देन CBA belongs to R cube, which is the domain, such that T of A, B, T of CBA, such that T of CBA is equal to ABC. ठीक है?
ABC.
So once we have a linear transformation which is 1 1 and on to, so it is an invertible linear transformation, thus we can find the inverse. So thus we can find the inverse linear transformation. Okay, now let's try to see what is the inverse. तो inverse निकालने के लिए हम इस तरह से करेंगे. Now this T of x, y, z, it belongs to R cube, which is the codomain space. Thus there exists, thus there is, suppose some z1, तो हम अगर थोड़ी सी अच्छी नोटेशन यूज करेंगे, सो देयर इज सम, सपोज हम यहाँ से कौन कैसा एलिमेंट चूज करेंगे, चलिए इस तरह से हम लिखते हैं, सपोज u1 u2 u3 belonging to R cube, such that this T of x y z जो हमने कोडोमेन से चूज किया, this will be equal to u1 u2 u3. ठीक है, so now this mapping T of x y z, it is defined as, so this gives, now how is this mapping defined? This is defined as, it is defined as z y x, the reverse z y x. So this is equal to u1 u2 u3, and this implies u1 is equal to z, u2 is equal to y, and u3 is equal to x. And then T inverse of u1 U2, U3. This is equal to, what is U1?
Z.
तो पहले T inverse of U1, U2, U3 is equal to X, Y, Z. इस तरह से X,
Y Z.
Z है ना इस इक्वेशन से यहाँ पे T inverse of U1, U2, U3 it is equal to X, Y, Z. लेकिन अब यहाँ पे जो हमारा X है that's equal to U3. Y is equal to U2. Z is equal to, तो इस तरह से इनवर्स एग्जैक्टली उसी तरह से डिफाइन हो जाएगी. Now let's take a different example and compute its inverse. तो इस तरह से हम मुझे लगता है अब आप ये कर सकते हैं. So let's put it as an exercise. So find the inverse of T from R3 into R3 defined by T of X, Y, Z. This is equal to X plus Y, Y plus Z, Z plus X. ठीक है, तो इनवर्स निकालने के लिए आपको क्या करना होगा? You first have to write that T of X, Y, Z, it belongs to the codomain space. So there is some element U1, U2, U3 in the codomain space such that T of X, Y, Z is equal to U1, U2, U3. And then this equation gives us T inverse of U1, U2, U3 is equal to X, Y, Z. But then using this definition, इसी definition को अगर हम use करेंगे, T of X, Y, Z is defined as X plus Y, Y plus Z, Z plus X. But now this is equal to U1, U2, U3. तो आपको 3 linear equations वहां पे बन जाएंगी in 3 variables X, Y and Z. तो वहां से आपको निकालने होंगे U1, U2 और U3 का value in terms of X, Y, Z, जिस तरह से हमने यहाँ पे किया. So then from this equation, T inverse of U1, U2, U3 it is equal to X, Y, Z. तो X का value substitute करेंगे in terms of U1, U2 and U3 and so on. And we will obtain the inverse of this linear transformation T. तो इसी तरह से second question and also find, आप कर सकते हो या मैं दिखाऊं?
सर दिखा.
चलिए ठीक है, एक दिखाएंगे. Defined by T of X, Y. This is equal to X plus Y, X minus 2X minus 3Y. तो इन दो में से कौन सा दिखाऊं मैं? मुझे लगता है सेकंड वाला, R square, ठीक है. तो वो फिर आप 3 वाला खुद ही करेंगे. So we have T from R square into R square divided by T of XY. This is equal to X plus Y, 2X minus 3Y. X plus Y, 2X minus 3Y. तो अब हमें निकालना होगा इसका इनवर्स. लेकिन इनवर्स निकालने के लिए पहले हमें वेरीफाई करना होगा that this linear transformation is a bijection. It is 1, 1 on. ठीक है. So this is a bijection. तो इसको वेरीफाई हम करेंगे. तो वेरीफाई करने के लिए पहले हमें दिखाना होगा दिस 1-1 मैपिंग and then we also have to show that it is an on-to mapping. So now to check, T is 1. तो बताइए किस तरह से हम चेक करेंगे that whether this mapping is 1-1 or not.
Kernel of T 0.
Exactly. And for this we find n of T. So now by definition we have n of T. It is a set of vectors X belonging to हम इस तरह से लिखेंगे, because now here we have the domain as R square, so it's a set of elements, suppose something like A comma B belonging to R square, such that T of AB equal to
0,
0,
0.
0. So that is if x plus y 2x minus 3y, this is equal to 0, 0. If and only if x plus y is equal to 0 and 2x minus 3y is equal to 0. Now this is a system of which is a linear homogeneous system. Now here this is linear homogeneous system. So then it has a non-zero solution. It has a non-zero solution if and only if determinant of A, which is equal to determinant of the matrix formed by the coefficients
1, 1, 2, minus 3. Minus
if and only if the determinant of the coefficient matrix
is not equal to
is not equal to 0. If and only if determinant of coefficient matrix is not equal to 0. So now determinant of the coefficient matrix is equal to 1, 1, 2, minus 3. What is the determinant? That is minus 5. It's not equal to 0. So thus the only solution is, तो कौन सा solution इसका xy is equal to 0, 0. 0, 0 is the only solution of this linear homogeneous system. So once we have 0 is the only solution, so this means that thus n of t is equal to 0. Thus t is 1, 1. हाँ क्या करना है फिर से? ये मैंने जल्दी से इसलिए किया क्योंकि आप ये बहुत अच्छी तरह से जानते हैं, ठीक है? या ये भी जल्दी हो गया? जल्दी तो नहीं किया मैंने?
No, sir. No, sir.
Okay, ठीक है. So we have t is 1, 1. Now how we will show that t is on to? Now since dimension of domain is equal to dimension of codomain, thus t is on to. Assalamu alaikum wa alaikum assalam. So thus t is on to and hence invertible. ठीक है. So now let t of xy is equal to u1 comma u2. So then x plus y 2x minus 3y, this is equal to u1 u2. So that is u1 is equal to x plus y and u2 is equal to 2x minus 3y. ठीक है? And these equations, this gives what does this give? तो यहाँ से हमें मिलेगा x is equal to 3 u1 plus u2 and y is equal to अगर यहाँ पे लिखेंगे x is equal to 3u1 plus u2, then we will get y is equal to, I think, minus 2u1 minus u2. ठीक है, यही मिलेगा। आपको समझ आया ये? मैंने डायरेक्ट इसका सोल्यूशन निकाला, लीनियर इक्वेशन को सॉल्व किया डायरेक्टली विदाउट राइटिंग सो मेनी स्टेप्स। तो ये आप देख लेना, अगर ये सही था तो फिर यही है। सो देन t of u1 u2, sorry, t inverse, this is equal to xy, and so this is equal to 3u1 plus u2 and minus 2u1 minus u2. This is the